Okay, so maybe we can continue. We lost our chair in the break. So, Thiago, it's a pleasure to have you here in the meeting, and he's going to be talking about crystal melting and the ADS3CFT2 avatar. So, Thiago, whenever you want.
Can you listen to me?
Yeah.
Is that okay? Okay, good, good. Well, start with the cliche. Thank you, the organizers. Very nice meeting, Latin American meeting. So I will start with this crystal melting, and in fact, the ADS3CF2 avatar will be an extra if you have time. So my goal is essentially to cite more often this book of Baxter, this fantastic book of Baxter, and that basically means that I want to find some integrable structures in string theory. There are some known examples of exactly solvable systems, subsystems inside string theory. Perhaps everybody here is familiar with the ADS5, n equals 4, and sometimes you can compute some correlation functions there. People say that ADS4 is integrable as well. The BMN limits, quite famous, and so on and so forth. My motivation here, this work started with the Nekrasov-Shatashvili limit and the gauge beta correspondence. I will give a very brief introduction to these ideas. And of course, these are unphysical models, right? These are basically toy models, and perhaps in the future you can find more realistic solutions inside this model. Let me put my clock here. And everything started here with Zeiberg-Witten system, right? We have some gauge theories. We start with n equals to gauge theories, and Zeiberg and Witten have shown that we can reduce the computations of very difficult computation in general for general theories. The computation of the Wilsonian effective theory is a very difficult problem. But in n equals to theories, this is basically the computation of this object called pre-potential. And Zeiberg-Witten have reduced the computation of this function to a monodromy problem. It's a problem in complex analysis. And moreover, they were able to, actually not Zeiberg-Witten, but later developments have shown that certain objects that appear in the computation of this pre-potential are related to certain objects in integrable systems. And today we have this nice table here. There are brain constructions, and this is a very beautiful subject. And Nekrasov and Shatashvili in 2009, they computed the quantum version of this, because Zeiberg-Witten computations are essentially classical. They related the field theory to classical integrable systems. And Nekrasov and Shatashvili were able to show the quantum equivalent of this calculation. And there, they compute this object. Is the can you see the mouse, the pointer in the mouse?
Yes.
Okay, good. And we compute this effective superpotential, and this effective superpotential is an object that appears in quantum integrable systems. This object is not important here, but it's called a Yangian function. And unfortunately, this topic is not very popular today. Nekrasov and Shatashvili wrote, oh, we are writing a second paper showing how this works, but today they haven't written anything. But they did generalize some of these ideas to n equals 4, to d equals 4, sorry, n equals to d equals 4 super Young Mills. Here you see that's 2 dimensions. But anyway, this is the motivation to this work. What we'd like to do is to understand a bit better this type of construction between integrable lattice and in one side and gauge theory the other side, and understand how it works for ADS CFT case. Nobody knows, and we'd like to see if we can build other examples and if you can generalize some of these ideas. Everything is open here. And I won't solve any of these problems today. Today, I'd like to present a game winner, in the sense that I'd like to study this system that we believe that's integrable. And it's game winner because, okay, I will explain it in a minute. But we have this Hamiltonian. It's essentially a statistical physics problem. Okay, it has been defined in this paper 12 years ago. And for one particular point, for the space of parameters for v equal to j, this Hamiltonian is equivalent to the quantization of plane partition counting, or as we call crystal melting problem, with one type of atom in this case. And evidently, this is a statistical physics problem. What would you like to do? Basically, we'd like to generalize, find eigenfunctions, eigenvalues. But this is a very hard problem. And then the second problem, it's a bit easier, but it's equally difficult. And sometimes the solution of this second problem is equivalent to the solution of the first problem, is to see if this system is integrable. That's the talk today. And why did I say that this is a game winner? It's a game winner because we would like to make a smart choice, right? I said that we'd like to connect an integrable system to gauge theory. And evidently, we could try to pick, open the book, this book of Baxter, pick a model there, a vertex model, 6 vertex model, and we can ask, okay, is there any gauge theory related to this problem, to this model? Evidently, this is a hard problem. It probably is not the smartest thing to do. We have chosen this problem because the classical solution, the classical problem, the plane partition counting, appears everywhere in gauge theory, in topological strings, in Seiberg-Witten theory as well. And total system is something that appears in Seiberg-Witten theory, AGT correspondence, geometric representation theory. That's a structure that appears in the Nekrasov-Shatashvili limit, and so on and so forth. So it's something that appears everywhere. And then we say, okay, well, perhaps since the classical problem is so important, perhaps the quantum problem has its corner, its importance somewhere. Okay, that was the main reasoning. And what does this Hamiltonian do, right? So consider first the problem in 2 dimensions, okay? This first term adds boxes in all available places in a Young Young diagram configuration. So this crystal melting is basically this plane partition in 2 dimensions equivalent to an integer partition. And integer partitions are represented by Young diagrams. And this Hamiltonian essentially puts one box in all available places in a Young diagram in 2 dimensions. This second terms removes boxes in all possible terms. This diagonal potential term counts the number of available places. In this case, we have 1, 2, 3, 6 places. And this second terms counts the number of boxes that we can remove consistently in a Young diagram. The nice thing about this 2D problem is that we can use some two-dimensional conformal field theory techniques in this case. I will explain in a minute how we'll do this, but using 3 fermions representations, we rewrite this Hamiltonian here as this. It's better. Okay, how we see this? So in order to see this, we basically fill all negative positions or negative label positions with particles, and all positive label positions are holes. Okay, and the creation of a particle, of a box, sorry, is basically the hopping of particle and hole hopping, and so on and so forth. So we have a very generic configuration here, and the creation of all these boxes are equivalent to many hoppings of particles and holes in this configuration. Okay. And if you write this, sorry.
Can I interrupt you, Thiago, for a second?
Yes.
So if I look at the Hamiltonian you have there in the green box,
this one, this
yeah,
one.
yeah, exactly.
Okay.
So can you walk me a bit through how this Hamiltonian creates a box or removes a box? Which term does what?
Yes. Suppose this is basically the free fermion quantization, the creation of, this is an exercise that you certainly did in your course of conformal field theories in 2 dimensions. So you remember that we can write this vacuum, okay? And we want to build the left and right Hilbert spaces, the Fock spaces for these 2 components, the holomorphic and anti-holomorphic. And then what I do is that I define this vacuum, and this vacuum, this 0, is equivalent to this configuration here. Okay, and this is annihilated by all psi star with any, sorry, there is a minus here, with okay. All with minus, and this is the vacuum. These operators are annihilation operators for negative n, and these are annihilation operator for all positive n's, but these components annihilate holes instead of particles. That's what I mean. And the Hilbert space in this case are built exactly like free fermion, Nevers-Schwarz fermions in 2-dimensional conformal field theories. Okay. In fact, this is basically 2-dimensional conformal field theory. Is that clear? Does it?
Yeah. Thank you.
And using SU2 generators, we rewrite this Hamiltonian as this guy, and many of you recognize this Hamiltonian. That's basically the XXZ model, but now with kink boundary conditions. The XXZ, or at least the XXX model with periodic boundary condition has been solved by Bethe in 1931. And the solution for this model with periodic kink boundary condition, by kink here, I mean that once you replace this system by the XXZ model, the particle here becomes the up spin up state, and the holes become the the down states. And kink means that for far left, we have up state, and for far right, we have down states. That's basically what kink means here. Okay, and here is what I was explaining to Carlos, because this Hamiltonian that I've shown is basically fermionic. It has this fermionic nature. And the states, these are the states lambda. These states are labeled by integer partitions, sorry. They are fermionic partitions, fermionic integer partitions. But in 2 dimensions, fermions and bosons are not really different, right? There is this fermion-boson correspondence, and I can write the bosonic generators, the bosonic components like this, and then I can build states which are in some way equivalent to this one. They represent the same Fock space, but now we build with bosonic generators. This is the statement of the fermion-boson correspondence. That's essentially this guy here. This is the current because the phi, this field phi is not well defined in 2 dimensions, but the derivative is, and this is, I define this current, and then I build this isomorphism between the bosonic and fermionic Fock state. The nice thing about this formula here is that, by the way, this is an equivalent way of defining the fermion-boson correspondence. Oftentimes, we find this correspondence in books. This is textbook material. Yes, Andres has a question.
Hi, Thiago. I just have a small question. Why you cannot generalize this correspondence to 4 dimensions? What is the problem? Because this looks purely kinematical.
No, but it is not. You mean this type of correspondence? Because you say that we have to say in general 2 Grassmann Grassmann numbers, and you can combine them and make something bosonic. But there are this cannot be reproduced for, it's an elementary fact, but the little group of SO2 that's relevant to 2 dimensions, the little group of SO2 is basically SO1. And your spin, when you try to construct the spins, this is a group theory explanation. But since the little group of SO2 is SO1, SO1 is basically trivial. And then you try to build your fermionic representation or spin representation, you see that it spins in 1 spatial dimension because this is 1 + 1 dimension. So you see that it's this idea of spin does not have any meaning in 2 dimensions. Or there is this Hilbert expression.
I understand this, but what I don't understand is because for this formula that you put here, I can do the same. Yeah,
yes, you can do this, and then I can give you a Hilbert space explanation. That this is what I have here. And in general, in 2 dimensions, we write this formula here. And so in 2 dimensions, I have this fermion-boson correspondence. And then you ask, okay, why can't we do this in 4 dimensions? The reason is that the fermion-boson correspondence is a quantum equivalence in the sense that the Hilbert space that we build with the fermionic fields is isomorphic to the Hilbert space, or the Fock space, actually, to the Fock space that we build with bosonic fields. This is the statement of the fermion-boson correspondence. This formula here is essentially a classical formula, right? You write, but the full-fledged correspondence is this one. It's a statement of Fock space. Does it answer your question? Or?
Yeah, I think that that's yeah. Then probably I think that you're trying to say that the subtlety comes in the demonstration of the isomorphism of the Fock space.
Yes. I'm not really sure I understood what you just said. Sorry, could you repeat?
Maybe we can leave the question for the discussion session.
Yes.
You can keep up with the presentation.
Anyway, but this is the statement of the correspondence, and we can write the bosonic states in terms of the fermionic states, and the coefficients are known. And okay, this is just one example since we have eaten some minutes. I will leave this example here, and we build more examples in this paper. Okay, then we would like to repeat part of this idea to 3 dimensions. So I should say that there is no trivial fermionic representation, in the sense that we have been able to write the 2-dimensional field theory, 2-dimensional model in terms of the XXZ model. The XXZ model is the integrability playground, so it's integrable, it's fine, we can build the eigenfunctions. It's very nice, there is a huge literature there. But 3 dimensions, we cannot do this. There is a fermionic representation, but in terms of stacks of spin chains. So this is the content of my second paper here. For 3 dimensions, we have the MacMahon function. This MacMahon function basically counts the number of configurations that I have with a given number of boxes. For example, I have just 1 vacuum, that's perfect. I have just 1 configuration with 1 box, 3 configurations with 2 boxes, 6 configurations with 3 boxes, and so on and so forth. And this is the generating function for this number of plane partitions. And one nice thing about these plane partitions is that I can write all these partitions in terms of a configuration of dimers. And these dimers are exactly solvable, but not Yang-Baxter solvable. There are different notions of exactly solvability. Here, I am much more interested in this idea of Yang-Baxter integrability. And then I have this, okay, can we solve this 3D system? Because this is the system I am interested in. And there are some conjectures here. They are integrable for this point. It's gapped. And these are conjectures. And there are some well-known facts. The ground state is given by this, and the norm square gives the MacMahon function. And this system is basically intrinsically fermionic. And then we want to play with these statements. I would like to show that this is integrable. I should say once again that we haven't been able to show that it's integrable. We collected many evidences. Probably for physicists, we have shown that it's integrable, but we discovered that mathematicians don't recognize our proof. What did we do? We wrote these plane partitions in terms of stacks of integer partitions. And we do know how the fermion boson correspondence works for integer partitions. So the fermion boson correspondence for plane partitions is basically the repetition, the product of many fermion boson correspondence for integer partitions. And then we found this formula here. This formula is not really important, but we can compute these coefficients exactly. And there is nothing important happening here. I just wrote this notation here just to make the computations easier. And then we ask, okay, what's the action of these operators on these states? Okay, and we computed the action of these operators, and they basically work like this. You build operators. This is the creation of operators for plane partition states, and we act this. These coefficients are, we we have an explicit formula for these coefficients, and they add boxes in all possible configurations, all possible ways, consistent ways. Consistent, I mean that it respects the plane partition rules. And the annihilation operators do exactly the opposite. They remove boxes in all consistent ways, and these amplitudes can be computed exactly. Okay, so now what we have an action of the Hamiltonian on plane partition states, on bosonic plane partition states, okay? And I claim that this is what we need to show quantum integrability of this Hamiltonian. And it's a short explanation of what I mean by quantum integrability. Quantum integrability means that if you are studying scattering amplitude process, a scattering process in a quantum field theory, and you say, okay, but you have now you have a statistical system, but even in the statistical physics, I can give this interpretation to the scattering amplitude. Of course, the objects there are not scattering of particles and so on. They are weights, statistical weights, and this type of thing. The S matrix, for example, will be equivalent to a Lax operator, but there is a map between these two ideas. But integrability means that if I have this scattering, there is no decay, no particle creation. Moments are basically reshuffled in the process. The incoming and outgoing moments are exactly the same. We just reshuffle. And the scattering amplitude is basically factorized into a product of two scattering amplitudes. Plus an additional constraint. And the constraint is that the three particle scattering, these three process, and evidently this one and this one, are exactly the same. And this is the statement, this additional constraint. And this constraint has a name, and it's a Yang-Baxter equation, my favorite equation. For these statistical models, we need to solve something else that's closely related to the Yang-Baxter equation, but it has the same RTT relation, very creative. And this RTT relation is a relation between this object, it's called Monogamy Matrix, and R matrix, again, very creative. That's a Yang-Baxter solution of the Yang-Baxter equation. And this guy is represented by a diagram of this. The number of the lines here is equivalent to the number of sites in your statistical system. And this monodromy matrix is, for those who know what classical integrability means, the trace of this monodromy matrix is the generating function of conserved charges. And this RTT relation, once you take the trace, is equivalent to the commutation of these conserved charges. That's the quantum equivalent of the Arnold-Liouville theorem.
You have 3 minutes left.
Okay. I'm finishing. And the Yangian, the RTT relation, if you expand in this way, is equivalent to this algebra. But now we have a Yangian, affine Yangian algebra. That's this beast. We have this crazy object. But the representation of this Yangian is amazing. It's really beautiful. It's exactly what we need. So these are the creation of boxes, annihilation of boxes, and this is diagonal term. And this is, you remember this slide is how the Hamiltonian acts. And then we have this conjecture that basically means that we have a map between we basically mean that this system that we are studying fulfill a representation of this MacMahon function. This is a conjecture, but it's still open. Okay. And then we'll be really fast here. This was 1 minute. Evidently, as I said, my original motivation was this Nekrasov, Shatashvili, KGBT correspondence, but as I also said that these plane partitions distance appear everywhere. And this is the ADS3 CFT2 correspondence, right? So suppose that we have a Chern-Simons formulation of this, and then we have here is the ADS3, and then we impose some boundary conditions. This is the usual Brown analysis. And the asymptotic symmetries of this space is given by the Virasoro algebra. And then we generalize this to SLN. And then we study again the asymptotic symmetries, and then we find WN algebras depending on the n. For the large n limit, we have an infinity number of generators with arbitrary number of spins. On top of that, we can add U1 current. And here are some examples of how this has been done. And then we try to build a representation of this. Then this is the usual representation of the Virasoro algebra, and you can open your favorite CFT book and you'll see that the Fermat module of Virasoro for the Virasoro algebra is labeled by Young diagrams, 2D Young diagrams. And Katz and Radu have shown that there is quasi-finite representation for W1 plus infinity algebra. And this quasi-finite representation is labeled by plane partitions. But of course, I said that we had Yangians, but now we have W1 plus infinity. The point is that there is a very nice isomorphism between these algebras. The Yangian, the affine Yangian algebra is equivalent to universal enveloping algebra of 1 plus infinity.
So there is a question by Gaston.
Yes, yes.
So I have two questions actually that are related because they are the two last things you mentioned. First of all, when you talk about the asymptotic symmetry algebra, I agree that if you started with SLN Chern-Simons, for instance, and then you make the standard reduction to the best Rubino-Witten, you get a higher spin theory after making a Hamiltonian reduction. So here, how Hamiltonian reduction gets related with this semi-finite representation is not clear to me, because you have to make a twist to go from the affine symmetry to the Kac-Moody or WN symmetry. So.
Okay. I'm not really sure I understand your question. You mean?
So I can repeat.
You want to know how this W algebras appears in this?
No. My question is more general. It's to make a contact with the gravity or higher spin interpretation. It's not enough to study these WN symmetries, because you have in the middle there is a Drinfeld-Sokol of Hamiltonian reduction.
Yes. I completely agree. This, in fact, was just a motivational.
Okay, but you are not describing gravity necessarily,
no.
right?
Yes, I completely agree. As I said, this is just a motivation. Okay, how this works in general is explained by Matthias Gabriel and Rajesh Gopakumar. In that paper, they do have a string theory, and they consider the tensionless limit of string theory on ADS3 cross S3 cross T4. And in this tensionless limit of the strings on that background, they were able to build this higher spin theory. Is that? Yes, I completely agree.
Yes, in that case, because the K goes to 1 in that case. It's a particular label.
Yes,
but I would hardly call this gravity, because this corresponds to the size in which the Planck length is equal to the size of ADS.
Mm-hmm. Well,
so
if you say this, I totally believe you. You are an expert on this. I am not. It's just a motivation for you. But as I said, this this that I explain here is just to give a motivation. How this works correctly is given by this paper of Matthias Gabriel.
Okay. And what about the relation with HCT? I agree that Nekrasov subpartition function, when you study Nekrasov subpartition function, it is natural to see how all this fits there. But this is in what regards to the n=2 four-dimensional Yang theory. What about the correspondence itself? How it shed light on the correspondence?
The Bethe gauge correspondence, you mean?
Yeah.
Oh, this is okay. In n=2,2 theory, you agree that I want to build the low energy limit of this theory, and this is completely characterized by the superpotential, this WEF. This has been shown by Witt and these old works, and you can find this that I'm about to tell in this book, this huge book of alpha mirror symmetry. There you can open this book and you will see that the exponential of the derivative of this superpotential on the scalar fields, on the sigma A, times 2 pi is equal to 1, okay? Okay. On the lattice system, we want to compute the Bethe-Ansatz equations, right? We want to find the eigenfunctions of this Hamiltonian, in this case, XXX Hamiltonian, the Heisenberg model. And I find this huge system of equations, that's the Bethe-Ansatz equations. But Young have shown that all these equations can be we can recast all these equations in terms of a potential function today it's called Yangian equation. This Yangian equation carries all information you need. And this Yangian equation satisfies an equivalent relation, the exponential of the derivative of these Yangian equations on the rapidities of your integrable system times 2 pi is equal to 1. And this led Nekrasov and Chatashvili conjecture that these systems are exactly the same. And in this sense, the rapidities of the integrable system are equal to the scalar fields in your theory. The spin of your lattice system is, anyway, there is a nice, I think that I run out of time. And okay, here I have a final message. And okay, I'd like to leave this quote here of Alexander Polyakov. Anyway, that's what I got for today.
Okay, so let's thank the speaker for this nice talk. I think that maybe we have time for a really quick question, if someone has one. Gaston, maybe?
Come on, he just took a long time to answer mine. I will not be monopolizing.
Let me ask one, and if it's not quick the answer, you can pass me to the discussion session. Is it clear to you how these discrete models, this sort of bosonization you present in the discrete models in higher dimensions translate to continuous?
Oh, this is a very good question. Actually, I do not know. I do not know. But the point is that there is something that I have considered, not your particular question, but the passage from these discrete systems to continuous systems, it's called shape limit, okay? Mm-hmm. And this shape limit is something related to okay, let me go back a little bit to the point. The classical systems, the classical plane partition systems are related to topological string theories on certain Calabi-Yau manifolds, okay? In this case, for this very trivial system, this is equivalent to C3, just C3, okay? And there is a conjecture of Vafa, Okonkov, and others that say that we can generalize this type of system. Once you map the plane partition system to Dymers model, topological strings are equivalent to other Dymers models, depending on the type of Calabial, New York Calabial, to other Dymers models in different lattice systems. In this case, I have a hexagon lattice, but if you put your Dymers in other lattice, then you get the other Calabial systems. And I have tried to find a way to compute this limit shape for other type of, for Dymers in other lattice systems, but I couldn't. This is a very difficult question. And in this sense, perhaps your question will be helpful, but I have no idea.
Okay, so let's thank the speaker once again.
Thank you.
And Gaston, if you want to continue.
Yeah, we have to, just since we have